Hello, chemists. This is Ms. Placino, and you're watching lesson 13.6 on electroplating. Today we're going to talk about how electroplating works, and this is really a very specific application of the electrolytic cells that we discussed in the previous lesson. So if you haven't watched that one yet, 13.5 might be a better place to start. Goals for today's lesson. You should be able to define what electroplating is and explain why we use it. You should be able to label the components of an electrolytic cell that we are using specifically for electroplating. And you should be able to perform calculations to determine what mass of metal will be electroplated onto an object. So definitely want to have your calculators handy. All right, let's dive in. So to help you visualize exactly what's happening during the process of electroplating, I want to start by showing this short video.
In this video, we're going to learn about electroplating. Electroplating is the process of coating one metal object with another. It works by electrolysis, which is when electricity is used to drive a chemical reaction. We're going to look at why you want to electroplate, how it works, and various conditions that need to be considered. So why would we want to do electroplating? Metals may be electroplated for aesthetics, protection, or both. Aesthetics might involve making a metal shinier or giving it an attractive colour by coating. For example, jewellery is often plated with gold or silver. A metal coating can be used for protection, as it may help resist corrosion, rusting, or just general wear and tear. Car rims are electroplated for both shininess and protection. Chromium, commonly known as chrome, nickel, tin, zinc, and cadmium are often used to plate copper, iron, and steel objects. Tin cans are actually made of steel, but have a thin tin coating. Ed White, the astronaut who made the first American spacewalk in 1965, was wearing a gold-plated visor to protect his eyes from the solar radiation. So how does electroplating work? An electric current is passed through a solution that conducts electricity, called an electrolyte. To create this current, two electrodes are dipped into the electrolyte solution and connected to a battery or power supply. So we end up with a setup that looks something like this. When the current is turned on, the electrodes gain a charge. The positively charged electrode is called the anode, and the negatively charged electrode is called the cathode. The electrodes in the electrolyte are carefully chosen based upon what metal you are plating with. So if you want to copper plate another metal, you will use a copper-based electrolyte solution and have a copper anode. The copper for the plating comes from the electrolyte solution, which in turn has its stocks replenished by the copper anode. So let's look at copper plating as an example. We want to copper plate some brass. So we have a copper anode, a brass cathode, and a copper-based solution for the electrolyte. So copper sulfate solution. Copper sulfate solution contains blue copper ions and colourless sulfate ions. The copper ions are positively charged and so are attracted to the negatively charged brass cathode. The copper ions deposit onto the brass, producing the thin copper plate. The positively charged copper ions gain electrons, which is known as reduction. The sulfate ions are negatively charged and so are attracted to the positively charged copper anode. The current supplied to the anode causes the copper atoms to oxidize, which is lose electrons, and then dissolve into the electrolyte solution. So the copper ions move from the anode to the cathode in the solution, and the electrons move from the anode to the cathode, but along the wire. The copper anode bar gradually dissolves to replenish the copper ions in the electrolyte solution, so the solution stays at the same concentration.
Hopefully the video gave you a good overview, kind of just of how electroplating works and what it looks like. I want to go into a little bit more detail here and really look at the redox reaction that is taking place. So here we have our general setup for an electroplating cell. We know it's an electrolytic cell because we have a voltage source. So again, we'll have a non-spontaneous chemical reaction taking place due to an outside source of energy. We have this metal electrode. This is going to be our anode in all cases. The anode in an electrolytic cell, as we talked about in the previous lesson, is the positive terminal. Sometimes in electroplating cell, this gets called the sacrificial anode, and that's because really its only purpose is to get eroded away to produce ions get them into the solution so they can eventually be plated onto whatever the cathode is. So the object to be plated, in this case the spoon, is the cathode, and that's going to be our negative terminal in our electrolytic cell, and we need an electrolytic solution. So a solution with ions present. In this case, we're looking at copper. So we'll have a copper electrode. Again, that's just going to be solid copper. Our electrolytic solution has got to contain copper 2+ ions. And our cathode is a spoon, but more generally speaking, just the object to be plated. All electroplating is, and the whole purpose of electroplating, is to deposit a thin layer of metal onto another object. And there are, two major reasons why we electroplate commonly, and then there's a third one that we'll also discuss very briefly. So they got into the idea of aesthetics in the video. So if you have a metal that's not particularly pretty, so if it is, kind of dull, it's not shiny and lustrous, you could electroplate it with a more aesthetically pleasing metal, maybe a gold or a silver, and make that object shiny. So we see that a lot with jewelry. Second application is for protection. So you can, they actually gave the example of chrome wheels. So the chromium is going to be less reactive than the base metals that they have underneath it. So if we coat that base metal that would react with the oxygen and kind of get corroded with something that is less reactive, that should protect the base metal and maintain structural integrity. So definitely put a star next to those two purposes. Those are the two most common. In industry, sometimes we'll electroplate to alter physical properties. This may change properties like conductivity, both heat and electrical conductivity. It might change adhesive forces. It might be able to alter friction between surfaces. But this definitely does not come up nearly as frequently when we're just discussing electroplating like in a typical chemistry classroom. So this is more of like a industrial application. Right. So let's dive into the electrochemistry that's taking place. We know, generally speaking, at the cathode, regardless of what type of electrochemical cell we're looking at, we always see reduction. The sign of the cathode in an electrolytic cell, which an electroplating cell is negative. In this case, we're working with copper. So we must have copper undergoing reduction, specifically the copper 2+ ions. So copper 2+ is going to end up as solid copper, an oxidation state of 0. The only way to accomplish this is to reduce those copper 2+ ions with 2 electrons. And this is the reaction that's taking place at the cathode, or in our diagram, taking place at the spoon. So the copper 2+ ions that are in solution get attracted to the spoon because it's going to have that negative charge once you have the power source running. And the copper 2+ ions are going to gain electrons and get deposited on the spoon as copper. We have to replace those copper 2+ ions that were in solution, and the way we do that is by sacrificing the anode. So we know at the anode, we see oxidation reactions, loss of electrons. The anode in our electrolytic cells is positive. So the oxidation reaction that must occur is copper getting oxidized to copper 2+. In order to balance out the charges, again, that's copper 0, I have to have 2 electrons on my product side. So what's going on there is the copper atoms, once that electrical current is applied, they're going to lose 2 electrons. They're going to go through the wire, and the copper ion is going to kind of come off into solution so that it can replace the ones that are being deposited onto the spoon. The balanced chemical reaction, the balanced redox reaction, kind of looks strange when we think about electroplating. We've got Cu2 plus Cu over on the reactant side. Our electrons cancel out. And then on the product side, we actually have the same exact thing. So we've got the anode replacing those Cu2 plus ions, and the copper atoms that were once a part of the anode essentially get transferred over to the cathode, to the spoon to plate it. So this is what you're going to see for all of your electroplating reactions, especially at this point in time, an ion and its metal on both sides of the reaction. Okay, so that kind of covers the chemistry that's going on in our electroplating cell. Let's take it a step further and try to make this quantitative and see if we can calculate how much metal, what mass of metal is going to be deposited onto our cathode, the object to be plated. So we can use the current, which we would measure in amperes. And the units for ampere are coulomb, which is a unit of charge over time, coulombs per second. And if you take the time that the object is plated for, so basically how long we're allowing the electroplating to go, we can calculate the mass of the metal deposited. So this is kind of crazy. We can essentially take time and turn it into mass, doing a handful of conversions. So this is definitely more of an advanced topic, but I think we can handle it, so we'll get into the calculation. All right, so what we're going to do is determine how many coulombs, again, just a unit of charge, will be emitted in 5 minutes with a current of 2 amps. So we've got some dimensional analysis to do here. I'll start by taking the information I'm given, 5 minutes, and I'll put it over 1 to keep my work organized. I know that amperes, another way to represent that is coulombs per second. So I've got a time unit in minutes. I can readily convert that into seconds. 1 minute is equal to 60 seconds. That'll allow me to cancel out minutes, and now I'm in seconds. I'm trying to figure out how many coulombs of charge would be produced. So let's use that 2 amperes. Coulombs over second. We should be able to calculate coulombs from here. Seconds cancel out. We can grind through that calculation and hopefully come up with 600 coulombs. All right, next we're going to take that number of coulombs and we're going to convert it into moles of electrons. And we can do that using Faraday's constant. We discussed Faraday's constant in lesson 13.3, talking about voltaic cells. The value is 96,485 coulombs per mole of electrons. So we've got 600 coulombs calculated from our previous step. And I want to turn this into moles of electrons. So let's see, I can put mole of electrons in the numerator. I'll put 96,485 coulombs in the denominator. I can do that calculation. And I come up with about 6.22 times 10 to the negative third moles of electrons. Our coulombs have canceled out, and that's how I've got the units mole of electron. Let me write that a little bit more neatly. There, that looks a little bit better. All right, so now we know how many moles of electrons are produced during that 5-minute span that we're electroplating. So how many moles of Cu2 plus could be reduced to copper? Basically, how many electrons would be required to do that? So I've got 6.22 times 10 to the negative third moles of electrons. And I want to get to moles of copper. So for every 2 moles of electrons, I can reduce 1 mole of Cu2 plus ions. And I guess we can technically take it out one more step. They're going to be like in the same ratio. A mole of copper 2 plus ions will get reduced to a mole of copper atoms. I'm not going to worry about that since there's not a big deal. So I can cross out my moles of electrons. I'm going to divide 6.22 times 10 to the third by 2 with 3.11 times 10 to the negative third moles. Cu2 plus. All right, finally, I'm going to take my moles of copper ions and I'm going to convert that into grams. Slide that up a little. 3.11 times 10 to the negative third moles of Cu2 plus. A mole of copper 2 plus and a mole of copper atoms have effectively the same mass. Losing those 2 electrons makes virtually no difference. So we can use mole of copper has a mass of 63.456 grams. Get our moles of copper to cancel out. And we should be able to calculate how many grams of copper would be deposited onto the zinc. So I'm coming up with 0.197 grams of copper. Oof. All right. So that probably seems like a lot of work. And yes, I agree. There are a lot of hoops to jump through. I want to try to take that process and let's turn it into a single step dimensional analysis instead of breaking it into all these little steps. So I can start with time. I know that I have 5 minutes of time. I'm going to put that over 1. I'm going to convert into seconds. And I'm going to use my 2 amps, which I know is coulombs over a second. And that's going to get me out of all my time units and into coulombs, a unit of charge. I need to get into moles of electrons next. And the connection between coulombs and moles of electrons is through Faraday's constant. That gets rid of the coulombs, leaves me with moles of electrons. I'm working with copper 2 plus. So there are 2 moles of electrons required to reduce 1 mole of copper 2 plus into just copper atoms. Get rid of my moles of electrons. And finally, if we have a mole of copper, and again, copper and copper 2 plus, their masses are plenty similar enough that we don't have to go through any additional work. 63.456 grams per mole is its molar mass. Moles cancel out, and I should be left with an answer in grams. So it's a little bit more of an involved dimensional analysis than what we've seen previously, but hopefully this is a skill that you've kind of been able to keep sharp with practice. And it's really all about making the units work. Right. So you've got some practice problems to work with to try to go through very similar calculations. You know I'm going to ask you to do this on your test, so it's definitely worth practicing and making sure you got the hang of it. All right, chemists, thanks for tuning in, and I hope you found this helpful.